Welcome back to the last video on linked lists, or on singly linked lists, excuse me. Next, we're talking about doubly linked lists, but we're done with singly linked lists, and I'm getting real tired of saying that word right now. So let's wrap up by talking about the big O notation of the common operations, things like insertion, deletion or removal, searching and accessing data, and also compare it to an array. And then we'll do a quick recap and move on to doubly linked lists, and at the end of that section, we'll do the same thing, where we'll compare not only doubly linked lists to arrays, but also to singly linked lists, and we'll see their unique strengths and weaknesses. All right, so let's start with insertion. In a singly linked list, inserting things is really easy, right? We either push it onto the very end. All that we had to do was take the current end, the tail, make a new node, and just set the tail.next to be that new node, and then update the tail. Same thing at the beginning. If we want to add something at the very beginning, we just make a new node and we set its .next to be the current head, and then move the head. So it takes constant time. It doesn't matter if our list is 1,000,000 items long or 10 items long. It takes the same amount of work, same amount of time to add in a new item. Now that's not the case with arrays. Remember that if an array is 1,000 or 1,000,000 items long, let's go with 1,000,000, and I add something to the very beginning, to the index 0, I have to shift every single index over and rewrite it all the way down to 1,000 or 1,000,001. Or if I add to the very end of an array, then yes, it takes constant time. But on average, if we were going to take the average, it's O of n, where n is the length of the array. So singly linked lists win that battle as far as inserting data, much faster, constant time versus an array where the average is O of n. Then we get to removal, taking things out of the linked list. And this depends on where we are removing from. If we're removing from the very beginning, super easy. That's O of 1, constant time. All that we do is, we've already seen, we take the current head and we just set its .next to be the next head, and then we take the old head and set its .next to be null. We chop that tie. But if we're removing from the very end, it becomes difficult in a singly linked list if we're popping, because we need to find the item right before the last item, right before the tail, and that involves iterating the entire list. So in our best case for removing from the beginning, it's O of 1. For the worst case of removing from the end, if there's 1,000,000 items, we're going to have to go, well, we're not going to have to go to the 1,000,000th. We're going to have to go to one before the 1,000,000th in order to remove that last item. Next up, searching. So searching through a linked list, if we're looking for a value, let's say that we're looking to see if the list contains 99. Worst case, that's O of n, where n is the length of the list, because it could be the very last thing or the second to last thing, and we would need to start at the very beginning and check every single node. So as the list grows, so does the amount of operations it takes to search for something. And the same is true of accessing, getting a certain node out. If we ask for the 10th node or the 100th or the 1,000,000th node, as that number grows, as the list grows, so does the number of operations there. When we compare that to an array has random access, meaning that it's constant time to access items once they're indexed. So the indexing takes time, and insertions can take time, and so can removals. But other than that, if you're just accessing, if you're asking for the 10th or the 50th or the 0th item in an array, it takes the same amount of time because of the way that arrays are structured. So arrays win that battle. So really, to wrap it up, singly linked lists excel at insertion and deletion compared to arrays. So if that's something that you're really concerned about and you don't need random access, you just need to have some data represented in a list with an order, but you don't need to just access the 50th item or the 1,000,000th item. You just need to access it in order. Then a linked list might be what you want if you're concerned about insertion and removal times and you don't care so much about random access. Okay. All right, so that's big O. Let's just recap a couple things. So linked lists, singly linked lists are an excellent, this is just what I said, excellent alternative to arrays when insertion and deletion at the beginning are frequently required. Remember that inserting at the end of an array is not a big deal. We don't have to reindex anything. Arrays contain a built-in index, whereas linked lists do not. Linked lists are just are nodes that are connected to one another with a .next, with a reference or a pointer. There is no number, there's no index or position. We can't access things easily using an index. And the last point that I'll make If you're wondering why would you use this, well, remember this is a course on data structures, and a lot of it is oriented sort of towards teaching theoretical things, but that doesn't mean that linked lists never have uses or applications. We'll discuss more as we go. We're going to learn about some more specialized data structures that are built on top of linked lists, like stacks and queues, which are coming up. And so we have to understand how linked lists work in order to implement a stack and a queue. Congratulations if you made it to this point. I know this is a lot of content. It's a little different than some of my other courses that are focused on building something cool or fun, or it's supposed to be fun at least. This could be a bit dry. So I highly recommend you take some time, take a break, do whatever you need to do, get ice cream or go yell in a pillow. And I'll see you in the next section. Doubly linked lists.